Alright guys, welcome to this page of the notes, and let's go ahead and take a look at graphing a radical function and how would be the best way for you guys to go about doing this. Now, we are going to need to set up an XY table to get some coordinate points that I can then plot, alright? But in order to find those coordinate points, remember there are values of the domain that are going to need to be excluded, and you're actually going to want to find those values first. So let me take my radicand, just what's under the square root symbol, and we set it greater than or equal to 0. So 3x plus 4 greater than or equal to 0, and I solve. 3x greater than or equal to 4, negative 4, and divide by 3. So x is greater than or equal to negative 4/3, which is approximately, if you were to use a calculator, it's approximately negative 1.3. It's actually negative 1.33333 repeating, but negative 1.3 because on graphing the coordinate plane that I've got, that's good enough. Now again, I told you I'd show you the number line just to help you visualize what's going on here. Remember, what you're doing is you're not eliminating or excluding negative numbers. You're only excluding numbers that make the radicand negative. The reason is because if the radicand is negative, I'm taking the square root of a negative number, which is imaginary, and not that imaginary numbers are bad, I'm not going to graph them. So here's what this is telling me. This is telling me that I have 1, 2, 3, negative 1, negative 2, negative 3. That the domain for my particular square root function, the one that I've given you up above, is this. My lowest value, my lowest domain value is negative 1.3, which is right about there-ish. It'll be a closed dot because x is greater than or equal to a negative 1.3, and then it's everybody greater than that. So everybody headed in this direction is part of my domain. I can use any of those values I want to. They're all going to give me a positive value. All right? Anybody less than negative 1.3 is going to give me the square root of a negative number, which is imaginary. I'm not going to graph imaginary numbers, so I exclude those values from my domain. All right? I'm not excluding negative numbers. Please notice, negative 1 is in my domain. I'm excluding numbers that make the radicand negative. All right? Excluding values that make the radicand negative so that I don't get any imaginary solutions. All right, so I know that I'm starting at negative 4/3, and that'll be the very first value up here in my chart. So x, y, minus 4/3. Now, the reason that I picked minus 4/3 is for this reason. I plug negative 4/3 into my function, right? So I plug in a negative 4/3. Well, 3 times a negative 4/3, the 3's will cancel each other out. I'm left with negative 4 plus 4. Negative 4 plus 4 is 0. What's the square root of 0? Well, the square root of 0 is 0. So what I have is my first ordered pair, or point that I'm going to plot, negative 4/3, 0. Now, a couple of quick things. When it comes to graphing, you're not the only one. I feel the exact same way. I don't really like graphing fractions or decimals. I much prefer to graph integers, right? Because I like being able to put my dot where that little grid lines up, which of course is wherever you have an integer. So, the next few values I put into my table, I'm not going to just pick anything that's bigger than negative 4/3, although I could, right? I certainly could pick a negative 1 and a 0 and a positive 1 and a positive 2 and a positive 3, right? And just pick those values and plug them in. But here's the issue that you would run into, right? What if you did? What if you chose x equals a positive 1, right? What if I did the domain value of positive 1? Well, let's check it. I plug a positive 1 in for x, right? 3 times 1 is 3. 3 plus 4 is 7. and you'd have to take the square root of 7, which is not a perfect square. That means the square root of 7 is going to come out to be an irrational number, a non-repeating decimal. And I don't want to graph that, or I ain't got time to graph that crazy decimal. This one's important because it's the lowest value in my domain, so I need that one. I can't really get around it, but I'm going to avoid other decimals if I can. So x equals positive 1 would not be a good choice. Let's take a look at another one. What if I picked 2? What if I chose x equals 2? Well, you plug a 2 in here. 3 times 2 is 6. 6 plus 4 is 10. And 10 is not a perfect square. The square root of 10 is a non-repeating decimal. It's an irrational number. I don't have time to graph those decimals. So here's what I would suggest you do. Let's work smarter, not harder. And right down here, you're going to go ahead and do a little bit of what I'll call side work. Okay, here's the beauty of this. You already know the first 10 or 12 perfect squares. You're not going to need all of them. You only need the first couple. You only need the ones that fit on the coordinate plane. So we're going to take our radicand, which is 3x plus 4, and I've already done my first perfect square, which was 0, right? When I set this guy equal to 0, I got x equals negative 4/3, right? I've already done that one. That one's in my chart, negative 4/3, and I got a y value of 0. My next perfect square is 1. So we're going to do 3x plus 4 is equal to 1. And solve for x. I subtract 4 to the other side, and I get 3x is equal to a minus 3, which means x is equal to a negative 1. Here's what this tells me. If I plug a negative 1 into my table for my next domain value, when I plug a negative 1 into the function, I'm going to get positive 1 as the result. Let me show you. Plug in a negative 1. 3 times a negative 1 is a negative 3. Negative 3 plus 4 is a positive 1. And the square root of positive 1 is 1. Right? Look at that. Those are integers. This is a nice, easy point to plot. Let's do a couple more. I've now done the perfect squares 0 and 1. My next perfect square is 4. 3x plus 4 is equal to 4. Why 4? Because 4 is a perfect square. If I can make this radicand equal to 4, I know my y value, my range value is going to be 2, because the square root of 4 is 2. Let's see if this comes out to be a nice one. 3x is equal to, subtract 4 to the other side, I get 0. X is equal, divide the 3, 0 divided by 3 is 0. So here we go. I know if I plug a domain value of 0 into my function, I'm going to get 4 under the radical symbol. So let's go back up here. I'm going to plug in a 0. 0 goes into my function. 3 times 0 is 0. 0 plus 4 is 4. And the square root of 4 is 2. That is a nice, neat, easy point to plot. I love it. Let's see if there's any more. The next perfect square after 4 is 9. So let's try 9. 3x plus 4 is equal to 9, which means 3x is equal to 5, which means x is equal to 5/3. Okay, all right. I know if I plug in 5/3, my radicand is going to be a 9, and the square root of 9 is 3. But 5/3 is not a nice, neat number, and I'm doing this because I don't want to graph decimals. So skip that one, ignore that one. That one doesn't work. Let's go to the next one, 16. Maybe that'll give me nice numbers. All right, 3x is equal to 16 minus 4 is going to be 12. Look at that. So I know the next one I'm going to want to do is plug a 4, a domain value of 4, into my function. So I'm going to plug in a 4. Right? 4 times 3 is 12. 12 plus 4 is 16. and the square root of 16 is 4. Again, I get another nice, neat number. Let's keep going. After 16, my next perfect square is 25. Here, let me move so I'm not scrolled down quite so far. Let me move right over here. So I'm going to do 3x plus 4 is equal to 25. It doesn't look like this one's going to come out nice. 24, let's get 20. Oh, whoa, holy cow, yeah. X is equal to 7. Look at that. Here's another good one. If I plug in x equal to 7, my radicand is going to come out to be a 25. The square root of 25 is 5. So there's another really good one. Let's plug that one in. If I make my domain value a 7, 7 times 3 is 21. 21 plus 4 is 25, and the square root of 25 is 5. All right, guys, that is more than enough points. Let's go ahead and graph these points and see what our function looks like. This is negative 1.3, which is probably right about there-ish. Then I have negative 1, 1 right there. 0, 2 right there. 4, 4. 1, 2, 3, 4. 4, and then 7, 5. Go ahead and connect those dots with a nice smooth curve. Make sure you extend your line all the way through the coordinate plane you've been given and put an arrow on the far end so that I know you know that guy just keeps going. This is where the graph starts, and it heads off in that direction to infinity. Right? Do not put an arrow on this end. Right? Don't put an arrow. Remember, this is where my radical function starts. If I go to the right of that point, I now have imaginary numbers, right? I have a negative radicand, which would give me an imaginary number, which I can't graph, right? I can't graph imaginary numbers. So that is my starting point. Then it goes off in the left, to the left from there. That's why I only have an arrow on one end. This is my starting point. I don't want to come to the right of that point. All right, guys, that takes care of this graphing problem. Again, the way it works, figure out, find the domain of your radicand, right? Exclude negative values so that we don't get imaginary numbers because I don't want to graph them. And then be really smart about the way you choose the points that you plug into your table. Head on over to the next page of the notes. We'll try another one of these together. I'll meet you guys there.